wonderful AP Statistics students. Welcome to another lesson in Unit 4, where we just wrapped up our probability ideas, and now we're moving into our random variables section of this unit. We're going to be covering notes 5 today over discrete and continuous random variables. So we're going to talk about what a random variable actually is. We're going to discuss the differences between discrete and continuous random variables, and then also talk about parameters that we use to help us describe these distributions. So grab a chair, grab your notes, get settled in, and let's go through this content together.
Okay. A random variable, a single random variable, is going to take on a numerical value that describe an outcome of some chance process. Okay, and all of these are going to involve the same probability rules we have already learned, but we're going to be able to extend those rules to model some larger events. Okay, let's look at an example that we have talked about before in order to get a gauge on these random variables. So suppose we toss a coin 3 times. Okay, we can imagine that, and we can draw out the sample space for the process. So let's go ahead and do that. We could do 3 tails in a row. Okay, flip a coin 3 times, we could get 3 tails. We could do tails, tails, heads. Tails, head, tails, and we're just going to list out all of the possible combinations here. Okay, I think I got all of those. We could do heads, 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 tails, heads, tails, heads, tails, heads, heads. Okay, and I think I got all of them there with that 8 then. So 8 different outcomes. Okay, so we're going to write that over here. Total number of outcomes 8. The probability of any one outcome is therefore 1/8, right? So like the probability we do 3 heads in a row, that's going to be a probability of 1/8. Okay, and these are the probability problems we've kind of worked with before. Now we're going to introduce a random variable. So I say let x, capital X, equal the number of heads out of 3 coin tosses. So x is going to be our random variable here, and it's going to define an outcome. And the outcome is the number of heads. So when x equals 0, that means the meaning behind that, we get no heads out of 3 tosses. Because that's our situation, is 3 coin tosses, right? So x equals 0, the meaning is we get no heads out of 3 tosses. And the probability we get no heads, there's only one event where that's an outcome, and it's the heads, heads, heads. So that probability is 1/8. Okay. When x equals 1, that's when we get 1 head out of 3 tosses. Now, what's that probability? Well, how many events did we get 1 head? Okay. And you don't have to circle this on your paper, but I'm just going to draw your attention to it. We get 1 head here, 1 head here, and 1 head here. Okay. So there are 3 outcomes where we get a single head. So 3 outcomes out of total 8. Okay. So that probability is therefore going to be 3/8. Okay, x equals 2. We get 2 heads out of 3 tosses. So we'll look back up at our sample space we drew out, and there are 3 instances where we get 2 heads, here, here, and here, 2 heads. 3 instances out of a possible 8 outcomes, so that probability is also going to be 3/8. And then the last one, x equals 3. We get 3 heads out of 3 tosses. And you can see that there's only one event where that happens. So that probability is 1/8. Okay. And that is the only 4 values that x can take. Okay. X can't be x equals 4 in this scenario. Okay, because the max is x equals 3, 3 heads in 3 coin tosses. X isn't taking decimal values. X in this situation can't be negative. So with our random variable here, we listed out our 4 possible x values, okay? And then with their corresponding probabilities, we can create both a frequency table and a histogram to describe this event. So a frequency table looks like that, and we just have our probabilities assigned to each of them. So we have X, which is our random variable, and then the probability of X, and that we fill in the table. We can also make a quick histogram here. So from 0 to 1, remember we go up to but not including 1. So this would be where X is 0. We have 1/8 as that probability. Between 1 and 2, it's up to but not including 2. So this would be when X equals 1. This next would be when X equals 2. And then this last little bit would be when X equals 3. Okay. So frequency table, histogram are both used to represent what we call a probability distribution. A probability distribution. Now, we've talked about how distribution is basically a visual of data before, right? The patterns that data can take. And that's exactly what a probability distribution is. It's the value our random variable can take and the probabilities associated with it. And by creating a probability distribution, you can start to see patterns and visuals of the situation that you have. Okay? So talking about probability distributions in general, there's a few what we call requirements or things that must be true in order to have a valid probability distribution. The random variable, it is a numerical random variable X. And most of the time it's called X, but you'll also see other various capital letters used, but we use X a lot. But it's a numerical outcome. It is not categorical, okay? And each of the values of X has an associated probability with it. Now, when I say it has to be numerical, here we were flipping coins, and obviously when we flip a coin, we get heads or tails, right? T or H. How is that numerical? Well, that part wasn't numerical. It's this part that has to be numerical. When you assign values to your random variable, they must be numerical, okay? Must be numerical. Okay. The sum of all the probabilities, what we call sigma of P of X. So if you add up all the probabilities in the probability distribution, it must equal 1. Okay, so if we go back up here, look at this frequency table. If you add up all of those probabilities, you'll see that they all add up to 1, okay? And that needs to be true in order to be a valid probability distribution. A probability distribution shows the value a random variable can take, and it must show all possible values that it takes along with their probabilities of each of them. So if it shows all possible values that it's going to take, the probabilities should all add up to 1 because you're accounting for all the events in the sample space. And then the last piece, each individual probability is going to be between 0 and 1. Okay. If it's exactly equal to 0, well, it's just not a possibility. If it's exactly equal to 1, then it's always going to happen. So, but each probability has to be between 0 and 1. Okay. So here's a couple of examples and just kind of getting used to the notation that we use with random variables. Okay, so you'll see here in this first row, we have the probability of X equaling 2. Okay, so what this means is what is the probability that the random variable equals 2? And I have a frequency table off to the right here that's the the frequency table we just made. So the probability X equals 2. X represented the number of heads in 3 coin tosses. And to find that probability, I look at the probability that it is assigned. So this probability is going to be equal to 3/8 here. Okay. Now the probability X is greater than or equal to 2. What is the probability that the random variable is greater than or equal to 2? Our random variable being coin tosses. So greater than or equal to 2, meaning including 2, and then everything greater than it, which there's only one random variable greater than 2, that's going to be 3. So to find these probabilities, I'm going to add up the 2 probabilities that I have there to get 1/2. And then the probability X is less than 1. Now, 1 is not included. It's just everything less than 1. Okay, so 1 is not included there. I don't have the line underneath my inequality, which means that this probability is equal to 1/8. Okay, so that's how we find some of these probabilities and then the notation that we kind of associate with them. Now, what we just worked with our coin tosses are called discrete random variables. Okay? So here's the thing about discrete random variables. A discrete random variable takes on a fixed possible set of values, and they only have whole number outcomes. You can have positive and negative outcomes, but only whole number outcomes. Okay? The random variables are usually the capital letters, like I said, X being the most common, Y, Z, G, B, I mean, any capital letter. Random variables themselves could be discrete or continuous. We're going to talk about continuous in the next section, but they can be discrete or continuous. They must be numeric, both discrete and continuous random variables. Okay, so even though the result of our heads, tails, coin toss is categorical, we describe that with a numerical outcome, the number of heads we get. Okay. With a discrete random variable, we have means and standard deviations we can also find and interpret. Okay, so the mean of a discrete random variable is the mean outcome for a theoretical infinitely many trials. When we find the mean of our discrete random variable, it is something we think about as expected value. Okay, an average value we would expect if the trials could continue indefinitely. Okay, it's not what we expect on a single trial. Okay, we're not going to interpret it that way. We don't expect this to happen on a single trial, but in infinitely many trials, this is the outcome we would expect. Okay, so I'm going to show you how to calculate it, and then we're going to apply it to a situation so you can actually see how we interpret it there. So the mean, the symbol is mu sub x. Okay, and that subscript is whatever your random variable is. So again, we use mostly x, but it might also be g, y, whatever it is. We also have the notation of it being an expected value. So the symbol for that is a capital E, parentheses x, that capital X in there. Okay, so the expected value, the mean, same thing, of a discrete random variable x is found by multiplying each possible value of x by its probability and then adding those all up. Okay, so in this little table, we're just going to kind of fill it in generally here. I got an x sub 1, an x sub 2, x sub 3, x sub 4, all the different values up to, we're going to call it x sub n. Okay, however many values of x you have, you could have 2, 3, 10, 20, however many values you have. Each of those is going to have a probability associated with it. P sub 1, P sub 2, all the way up to P sub n. Okay. To find that expected value, you take that numerical outcome and you're going to multiply it by the probability it is associated with. And then you're going to add that to the next value times its associated probability, all the way up to the very last one, x sub n times p sub n. Okay. And what that looks like in notation, mu sub x is equal to the expected value. We add up this multiplication pattern, so we're going to use sigma, and it's going to be xi pi. So for each individual x times its individual probability. Okay. And I always like doing this in an example because I think it just clicks a lot better when we see an example of this in action. So that's what I have on the next page before we discuss standard deviation at all. Let's make sure we understand what this means with the expected value. So Northwestern posts the grade distributions for its courses online. In the Stats 101 class, there is this distribution, the most recent one. Part A wants us to create a probability distribution for the random variable x, which represents a student's grade on a 4-point scale, meaning an A would be a 4, 3 would be a B, 2 a C, 1 a D, and 0 would be an F. Okay, so that's going to be our numerical outcome. So I'm going to write X and then the probability of X. Now the order that you write these in is up to you. Okay, you could write this as 0, 1, 2, 3, 4, or it's not a big deal if you write it as 4, 3, 2, 1, 0. Okay, you could really write this either way. They're not picky about it on the AP exam. The only thing that might trip you up it would be if you did go to make a graph or a histogram. Obviously, you're going to want to make sure your X values are in numerical order. Okay, that would be the only thing. So I'm going to go ahead and do it in numerical order, but not a big deal if you start at 4 and go down from there. Okay, so a 0. When X equals 0, that represented getting an F in the class. So I'm going to put 0.02 because that's the percentage of Fs in the course. X equals 1 represented a D, so that's going to be 0.1 for that probability. 2 represented a C, which was 0.2. 3 represented a B, which was 0.42. And then a 4 represented an A, that was 0.26. Okay. And let me just double check this real quick. If you add all of these up, you should get 1. Yep. I added them all up. I get a 1. It is a true probability distribution here. Part B, find and interpret the probability X is greater than or equal to 3 if X represents a randomly selected stat student. So if we randomly select a Statistics 101 student, what is the probability that they have a 3 or higher? Okay, so let's find the probability and then we're going to interpret it. So X greater than or equal to 3, it means getting the value of 3 or any X value higher. So getting the value of 3 would be 0.42. And then the only X value higher is the 4. So we would add the 0.26, the probability associated with a 4. And that's going to give us 0.68 as that probability. Okay. Now, interpreting it, we would say the probability, and we want to put context, remember, in our interpretations. We don't just want to write out the probability X is greater than or equal to 3 is 0.68. That is not a good interpretation. Any interpretation we do, we want to include the context. So the probability that a randomly selected Stat 101 student, and then we want to interpret what X being greater than or equal to 3 means, okay? A 3 meant that you got a B. A 4 meant that you got an A. So this interpretation means that they gets a grade of a B or A is 0.68, okay? That's what that actual probability in symbols meant, okay? C, write the event the student got a grade worse than a C in terms of that random variable and find that probability, okay? So there's actually 2 ways we can write this, okay? And that's where discrete random variables become fun. So think about the student got a grade worse than a C. So a C would be a 2 on our random, and then worse than a C would be less than 2. So that's one way we could write this. The probability that your grade is less than 2. Because in the wording, we're not including a C in the grade that the student got. What we could also write, and you don't have to write both every time. You can just pick one or the other, but I just want to point out there's 2 ways of writing this. For a discrete random variable, we could also write the student got a grade worse than a C. That means that they got a D or an F. Okay, so if they got a D or an F, we could also write that as less than or equal to 1. Okay, because that also means that they got a D or an F, which they got a grade worse than a C. Okay. Now, based on the wording, you'll probably usually write it like this in situations where the student got a grade worse than a C. You usually think to include the C, which is represented as a 2 in your answer, and that's totally fine. But I just want to point out how both of these for discrete random variable are going to be the same value, okay? Both are going to be the same value. We're going to find them both the same way. We're going to add up the probability a student gets a D with the probability the student gets an F. and we get 0.12 as that probability. Okay, the last piece, compute the mean and interpret the value in context. Okay, so I will talk about how to find this on your TI 84, but let's do it by hand just so we can appreciate doing it by hand. So the mean of our random variable, or the expected value of our random variable, we're going to take our first x value, which is 0, and we're going to multiply it by that associated probability. Okay. Now I know this comes out to 0 anyway, but it's the formula, just work with me here. Okay, plus 1 times that probability of 0.1, plus 2 times that probability of 0.2, 3 times the probability of getting a 3, plus 4 times the probability of getting a 4. We multiply those, add them all up, we get 2.8, okay, as our expected value of x. Now, just like way back in Unit 1, we had the conversation about how sometimes means it takes on decimal form, even though your variable might be discrete, right? So like think back to like number of siblings. When we had the number of siblings, we averaged the number of siblings that our classmates had, and it ended up being a decimal. And it doesn't make sense to have like 1.2 of number of siblings, but we said that's just how the average works, right? It's the same thing here, okay? When we go to interpret it, it might sound a little weird because how do you get 2.8 on the grading scale when you have discrete values? But that's just what the consequence of the mean here, okay? So we would say if many students took this course, we would expect an average grade of 2.8. And I have to put some context to that there. I can't just end it there, which is between A, B, and AC. Okay. Always put the context that goes along with it. Okay. That's rule number 1 of interpreting. And then for this interpretation, also notice how I said if many students took this course, which implies that indefinitely many trials. That is part of the interpretation of the expected value. Okay. With mean also comes standard deviation. Okay. The standard deviation, it's a measure of how much the values typically vary from the expected value, much like the regular interpretation of standard deviation here. So the formulas for this also look a little strange. Again, we're gonna I'm going to show you the formula. We're going to find the example by hand, but there is a quicker way. We'll do this on our calculator eventually. You know, we got to understand the formulas, okay? And the only way to understand the formulas is just to sometimes to do them by hand, okay? So notice I have sigma x squared, okay? So that should be a clue. If I have sigma x squared, we're talking about variance, okay? So we're going to find the variance first, and then to go from variance to standard deviation, like we always do, we just are going to square root it, okay? So how we find the variance first? It's a good time. We're going to take our first x value. We are going to subtract the expected value, the mean, okay, to figure out that distance from the mean. We're going to square it, and then we're going to multiply by that individual probability, okay? And that's the first piece. We're going to add that to the same thing, but with the second x value and the second probability. And we're going to do that with all of the values of x, all the way up to x sub n minus mu sub x squared times b sub n. Okay. Now the formula for this, again, sigma sub x squared, we say var of x. Now we usually don't use variance as much in this algebra-based AP statistics course, if I can say it correctly. Use variance a lot more on the calculus-based. But for us right now, just think of variance as this intermediate step here. It's the sum of all the individual x values minus the mean squared times the probability. Okay, and then to find the standard deviation, we just square root that whole formula. Okay, and that's where we get this formula from. Beautiful thing that it is. Okay. And then a quick little demonstration of it for the Northwestern example above. Let's find and interpret that standard deviation. Okay, so we're going to start off finding this variance. I'm going to leave off the square root for a hot moment here. We're going to start with 0. We're going to subtract that expected value we found and multiply it by that probability. Okay, so 0 is a grade of F, had 0.02 probability associated with it. Okay, plus the grade of a D, plus the grade of a C, plus the grade of a B, plus the grade of an A. Very fun. If you want to pause and make sure you can do that on the calculator, go for it. What you should get, though, is a 1. Now, why that is so nice, we'll never know. Okay, but it's a nice one. So when I go to square root it, it just works out so beautifully into another 1. And that's our standard deviation, is 1. Okay, now what does that mean? We have to interpret that as well. All right, so interpreting the standard deviation, we would expect, okay, because a 1 represents a 1 letter grade increment. If our standard deviation ended up being like 0.5, I would say the typical deviation from the expected letter grade to be 0.5 or less than 1 letter grade. Okay, or if it was 1.5, we would say or more than 1 letter grade. But we want to put context to whatever that number is. Okay, don't forget the context. Okay, that's discrete random variables. Let's have a short conversation about the continuous random variable. We're not going to use a lot of continuous random variables in this unit. We're going to introduce them. We'll use them more in Unit 5, okay? But a continuous random variable is just like continuous variables in general. They take on all possible values in an interval of numbers. Okay. The probability distribution is described by a density curve. Okay. Continuous random variables are usually described with functions, okay, and functions on the coordinate plane. Okay, the probability of any event is the area under the density curve, whether it's above, below, or between values that define that event. Okay, the area is always equal to 1 underneath the entire density curve. Okay. Probability is on the y-axis. So finding the area equates to finding the probability in an interval of numbers. Okay. The probability at an event is actually 0 for a continuous random variable because the area under a single point is actually 0. Okay? And again, that's kind of getting more into the calculus side of statistics, which we will not approach. But when we do talk about our continuous random variable, you'll see that we always define x as an interval of values. The continuous random variable we are going to be discussing we'll start off in Unit 5, and we'll talk about the normal random variable. Okay. The mean and standard deviation are found actually using integration, and because of that, the mean and standard deviation are unique for each set of density curves that you can create. So again, we're not going to discuss the formulas here. They're not super general formulas that we are going to be able to apply. We'll talk about mean and standard deviation when we get into our normal random variables. Okay. So again, I make a note at the start of Unit 5. That's when we're going to get into these a little bit more. Okay. The last thing I want to comment on before we wrap up this section of notes is just, why do we have these? Okay, why did we all of a sudden introduce these, especially after our conversation on probability? But random variables help us represent more things than just a single measurement can. So when we were looking at probability before, we were looking at the probability of a single event, okay, or 2 events occurring together. And That's great, but we want to use random variables to apply situations where you have many possible outcomes, and it lets us use theory to apply to those real situations.
And that wraps up our lesson on Notes 5, Discrete and Continuous Random Variables. Thank you guys so much for following along. If you have liked this video, please hit the like button and subscribe to my YouTube channel for more great AP statistics content. And I will see you in the next video, but until then, I do wish you endless statistical success, and we'll have fun in Note 6.